Hi, my name is Ahmad Talai. The International Panel on Climate Change (IPCC) has recognized the parameterization of snowfall velocity as one of the most important determinants of climate sensitivity. The existing fall velocity parameterizations that are derived from measurement in stationary air are still used as a representation of the average fall velocity in turbulent air, and no current forecasting model treats the snowflakes otherwise. Uncertainties about the effect of atmospheric turbulence on cloud-based microphysical processes such as droplet growth, precipitation development, and precipitation rate reduces our understanding about cloud lifetime, cloud formation, and local and global climate prediction. And today, I'm going to introduce you to a generalized formulation of equation of motion for snowflakes moving in a turbulent flow. So this next slide here, I'm showing the outline. So first I'm going to talk about the multi-angle snowflake camera and then the statement of the problem. And then I will walk you through the analytical solutions that I developed for the Navier-Stokes equation. And then I will introduce the revised equation of motion. So next slide. Turbulence changes a uniform distribution of cloud droplets and concentrates them along with large eddies. This could increase the collision efficiency of cloud droplets. So turbulence could accelerate the formation of large droplets and expedite the precipitation. Here I'm going to show the formation of different flow regime around the free-falling sphere. The flow around the sphere is initially laminar with no wake. With increasing the particle velocity, the flow behind the sphere broadens and the stationary region behind the sphere develops. As the particle continues to increase its velocity, a pair of circulating eddies behind the sphere develops due to the fluid viscosity. At higher speeds, it develops unsteady vortex shedding, but usually snowflakes do not pass this stage. Snowflakes are so light, so atmospheric turbulence can change their trajectory and fall velocity. The surface-based multi-angle snowflake camera takes high-resolution images of the snowflakes while simultaneously measuring their fall velocity. The fall velocity is calculated from the time it takes to traverse the distance between upper and lower triggering array. So here you see the mask. I'm showing here the surface-based mask. It consists, as you see, it has three cameras separated by 33 degrees. It takes high-resolution images while simultaneously measuring the fall velocity. And next, I'm showing some example. So you see this is an example of snowflake captured by mask from three different views. By analyzing the images, we get some properties of the snowflakes like maximum dimension, area, complexity, orientation, fall velocity, and so on. Basically, mask provides us the geometrical and dynamical property of snowflakes. And this is just an example of the images captured by mask in Alektok Point, Alaska between 2014 and 2017. Particles demonstrate a wide range of size and shape from small, near spherical droplet-like particles to large, complex aggregate structure. Next, snowflakes are continuously interacting with atmospheric turbulence. Vorticity can trap them or reduce their fall velocity. Snowflakes can also accelerate if they follow the large eddies. This broadens the velocity distribution of the snowflakes. Snowflakes get a different fall velocity distribution when the wind fence is installed in the mask. The wind fence basically reduces the turbulence interaction with the snowflake, and as a result, the mask measures approximately the fall velocity in a stationary air. So the fall velocity gets a local peak at about 1 meter per second. So here you see the actual images of the mask with and without wind chill, and these are on the right side you see the plot, so the actual data. As you can see, the peak reduces if we take off the wind fence around the mask. Now the problem is developing an equation of motion suitable for application to a broader range of Reynolds number. We'll see that snowflakes, they have a very broad range of Reynolds number. So we need to develop an equation that can be useful in this broad range of Reynolds number and can predict the particle trajectory and fall velocity in any non-stationary flow like turbulent flow. So I have to say that this is an old but it's a challenging problem, and then it actually requires finding a solution to the Navier-Stokes equation, one of the 7 millennium problems in mathematics. So it's still active. Equation of motion, basically for a particle that is moving in any flow, the equation of motion considers all the forces acting on the particle. For example, here I'm showing the Maxwell-Riley equation, one of the famous equation of motions. On the left side, you see it's just the mass of the particle multiplied by acceleration, so it's Newton's second law. P denotes the particle, F for the flow. On the right side, you see the particles are falling due to the gravity, here expressed in the buoyancy form. And then we have a stress gradient of the float on the absence of the particle, and then we get virtual mass. And these two terms in the bottom, the first one is the steady drag and unsteady drag. So we'll talk about these terms in more details in the next slides. But I have to say that the Maxwell-Riley equation of motion works only for the particle that starts from rest and also has a Reynolds number less than 1. However, as you can see here, this blue line shows that the Reynolds number range of the snowflakes are between 1 and 1000, so we need to modify this equation. So my approach to modify the equation of motion was to first solve the Navier-Stokes equation and find the flow, and then see how much drag is exerted from the flow, the viscous flow on the particle, and from there modify the equation. So by substitution of the variable eta equal to r, and this here you see this is the Navier-Stokes equation. Basically, it's expressed in the stream function. It's the same Navier-Stokes equation. By substitution of variable eta r sine of theta, I noticed that these two terms on the right hand side, they cancel each other. So what remains is just the linear component of the Navier-Stokes equation, which is easy to solve. And I found the solution which looks like this. Here J1 is the Bessel function of the first kind, and Y1 is the Bessel function of the second kind. Here's the solution again. And here I visualize the velocity field using these velocity components that I got from the solution. At sigma 0.7, solution creates a vortex, as you see here on the right hand side. By increasing the value of sigma, it splits and becomes two pair of vortices. It's just so this is just for illustration, show that the solution works. The Bessel function is able to reduce the eddies and vorticities. So the dimensional analysis suggests that this sigma here should be a function of square root of Reynolds number divided by a. And I define sigma initially like this. So then the time functionality of the solution becomes proportional to the particle velocity. This is a term that I use to modify the equation. So if you recall the Bassett drag, which comes from here, this is the same drag that was used in Maxwell-Riley equation for low Reynolds numbers. It contains only viscosity. So what I did, I noticed that higher Reynolds numbers, nonlinear terms, appear because of that velocity of the particle. So from the solution, I added that term over there. And as you see, this is a modified form of the equation of motion that I found. And here I'm showing some simulations. So this simulation basically, the background is the turbulent flow, and these white dots are the particles, very small particles, 0.5 millimeter. They are interacting with the background turbulent flow. And as you see, the turbulent flow clusters them. So the homogeneous distribution disappears. And then these particles, as they cluster, they get the chance of the collision increases. I will show it in the next slide. But here I have ignored the collision between the particles. So these particles are just interacting with the flow continuously, as you can see here. And the large eddies basically, these particles basically interact mostly with large eddies. These eddies pushes the particles away, so that's why we get the concentration here. And at the end, you see we have such a big, large eddy, and these particles basically follow these eddies. And in the next slide here, that's the same concept. Here I allow particles to collide, and as you see, they are growing. The size of the particles are growing as they collide. So let me start from the beginning. As you see, the turbulence initially clusters them, and then the collision efficiency increases, and then we see the precipitation here. So as the particles are increasing, they are gaining more mass, and then they're just falling straight. They don't interact with the turbulent flow because turbulent flow doesn't have that much kinetic energy to change their trajectory. With that, here is my conclusion. So the data show that the snowflakes have a Reynolds number between 1 and 1000. In this range, we need to modify the equation of motion, and by solution to the Navier-Stokes equation, I was able to fix it.